Hello, today we're going to go over Chapter 14, Section 2. We are talking about chemical kinetics, or the rates of reactions. Some reactions occur slowly, like the rusting of iron. You're going to fill in your own example here. You can steal mine if you'd like. So rusting of iron takes days or weeks or months to occur, versus something that can happen much more quickly, such as the combustion of hydrogen gas. So hydrogen, like a balloon, for example, in oxygen, is going to react very quickly, and then that reaction will be over. So it's a very rapid reaction in probably seconds versus days or weeks. This section explains why, and we're going to learn to calculate the rate of a reaction. The rate of a chemical reaction is a measure of the change in concentration over or per the change in time. So it's written out right here. R is the rate. Delta X is the change in concentration. Sometimes it's also written as delta C over delta T, and lowercase t is for time. So for our example reaction, we have hydrogen gas reacting with iodine gas to make hydrogen iodide. And the rate of the reaction, how quickly this is occurring, can be described based on either reactant or the product. So it's the change in concentration of, pick one of these things, over the change in time. So if we are looking at hydrogen, for example, let me make up some numbers. If I start with 100 molecules, we don't measure it, concentration of molecules usually, but let's just say we had 100 molecules, and those molecules are combining with the iodine surrounding it, and it goes down to 25 molecules. The change in concentration is going to be 75 in my made-up example. So 75 molecules have turned into HI. And the change in time, I haven't told you, so we would need to know how long passed since this happened. And let's say that it took 10 seconds just to keep the numbers easy. So the rate of that reaction would be the change in concentration, or 75, rate equals delta C over delta T. And for this specifically, hydrogen, it went down by 75. So the change was 75 over 10 seconds. And this is molecules. We want to put our units. So that would be 75 divided by 10, 7.5 molecules are reacting per second. Okay, so that is the rate of the reaction. What would be the rate if we were looking at the iodine? Well, for every one molecule of hydrogen, one molecule of iodine also had to be used up. So it's a 1-to-1 mole ratio, and molecules is the same thing. So it's a 1-to-1 ratio of the molecules, which makes it a 1-to-1 ratio of the moles of these substances. So the rate of iodine would be exactly the same number. This is the rate of the reaction. We calculated it with respect to hydrogen, but it would be the exact same number for iodine. Okay, now here's the tricky part. What we always do is we always want the rate. Let me write this. Where can I squeeze this? Let's write it up here. The rate is for 1 mole of reactant or product, and is always positive. And there's Simba. So it's always going to be a positive value. If you get a negative, just take the absolute value of that. So it's always positive, and it's for 1 mole. Since the coefficient of hydrogen is 1, this is the rate of the reaction. And the coefficient of iodine is also 1. So this is the rate of iodine disappearing. Hello, Simba. the HI, hydrogen iodide, is forming 2 molecules for every one of these. So if 75 molecules were used up, if this goes down by 75, this one went up by 150. So for the rate of the reaction, okay, the rate can't be different. For a reaction to occur, it's happening at the same rate. So we have to somehow fix this. So stick with me here. Okay, it's not as hard as it sounds. If the change in HI is 150, okay, and it's increasing, that amount is going up. So it started with none and it went up to 150. Over the same 10 seconds, I would get 15 as the rate of my reaction, 15 molecules per second. But I want it to match up. So what we have to do is we want for 1 mole of reactant or product. So we're going to take whatever the coefficient is and put 1 over that coefficient. So it's going to be 1 over 2 in this example, which then would give us the same value. It's half of 15, which is 7.5 molecules per second. So that's how we're going to find the rate. And this is a very generic rate equation. So if they give you a change in concentration and a change in time, this is how we're going to calculate it. And we're going to go over this several more times. So if you're a little confused, don't worry. How do we write these out? Okay, well, if I were to not have made up numbers like 100 molecules and 25 molecules, if I just wanted to write it as delta H, I could write it like that. And it's going to be over delta T. Now, remember when we find the change in concentration, we're going to have the final concentration minus the initial. So for hydrogen, it went down from 100 to 25 in my made up example. 25 minus 100 technically would be negative 75 molecules. And we can't have that because we want it to be positive. So it's going to be the negative change in concentration of, and I shouldn't have put delta H because that looks like enthalpy and I don't want to confuse you guys later. That's what I'm thinking of. It's in brackets, the concentration of H2 gas. There we go. Were you guys yelling at the screen? I hope so. That's the change in the concentration. Remember brackets? Bracket equals concentration in molarity, capital M. That's what the brackets around the formula mean. Okay, so that is the rate according to hydrogen. This is all in your book, by the way, on page 625. If I wanted to describe the rate with regards to iodine, it would be the change in concentration of iodine over the change in time. And I keep forgetting those brackets. Don't let me do that. And then it's going to be 1 over the coefficient, which is 1. And I did not write that up here, but it's 1 over 1, which makes it just a negative value. I can erase this part to simplify it, right? Because 1 over 1 is just 1. Where it's going to matter a lot more is right here. The change in concentration of HI over the change in time, delta T, has to be fixed because you're making twice as much. So it's 1/2. And since this is a product, it's being formed. So the amount of the product is always going up. So the change is going to be positive. So this time we don't need that negative out in front. So if it's a reactant, it has a negative in front. If it's a product, it does not. Okay. And hopefully this graph will help stuff sink in a little bit more. This is figure 14.2 on page 625. We have the concentration in molarity increasing as we go up. And down here, this is time in seconds. So for our examples here, let's do hydrogen. This is 1, this is 0, and let me do hydrogen in, looks like it's in green in your book. H2, concentration of H2. I started randomly at 100 molecules. The book uses 1 molar as the starting concentration. And what's going to happen is it's going to go down. Okay, the concentration decreases. And this is not a straight line, it is a curve. There's a reason for that. We'll talk about that in a second. Okay, it goes down something like that. And then in red, the concentration of HI is going to look a little different. The concentration of iodine is going to change more quickly. So it's going to look something like this. Okay. And how can I tell the rate and what is going on? So what this is meant to show you is that the concentration is either going up if it's the product or going down if it's a reactant over a given amount of time. It's not a straight line, and that is because the rate of the reaction depends on where you are at. So at the very beginning, at time 0 down here, when T is 0, the reaction is happening fastest. The rate, change in concentration over change in time, that is rise over run in this graph. And you guys should recognize rise over run as the slope of the line. So notice it starts out very steep. It's a very steep slope because it has a high rate. And then as we go farther along in the reaction, it starts to kind of level off and the slope becomes very small because the rate is becoming small. So why is that? Why do reactions happen very quickly in the beginning and then slow down towards the end? Think of like your little volcano when you were in elementary school and you filled it with vinegar. So you have your little bottle in here and you filled it with vinegar and then you added your baking soda or vice versa. And it starts erupting really, really quickly all over the place, right? So all that fake lava is coming out and then it slowly slows down and less lava is being produced and then it stops. Why does it go really fast at the beginning and slow near the end? If you said concentration, you are correct. So the higher the concentration, here we have a concentration at the highest point of 1, the higher the concentration, the faster it will react. That has to do with the video we watched. If there are more people bumping around, more molecules bumping around, they will react faster. As you make more and more product, this HI, so as the product goes up, you have more and more couples. Oh, that works with this example as well. You have more and more HI paired up. That means that there are less singletons to bump into each other. So as your concentration goes down because it's reacting, the rate slows down because there's less things to bump into each other and turn into our product. Okay, hopefully that makes sense. So another way of looking at the rate, we just wrote out these equations, is the slope of this graph right here. And the average rate of the reaction, I'm getting this out of your book, the average rate of a reaction for a generic equation. So instead of our example, let's use a generic equation where we have A, and I'm going to make this a different color. Let's make it purple. A plus B, the little lowercase, is the coefficient. So 1 or 2 or 3 forms C plus D. Okay, so Capital is whatever the compound is. So up here, A was hydrogen, B was iodine, and C was HI. There is no D because there's only one product here. Okay, but if we have this reaction going on, the rate, the average rate, can be written as negative, okay, because we're going to look at A, change in A over change in time, concentration of A, keep doing that. And remember, we have to adjust it based on this coefficient. So it's 1 over the coefficient. Okay, we're multiplying these two things together. So negative 1 over A times the change in concentration of A over the change in time. That is going to be the same rate that we use up B. Negative 1 over B, the coefficient B, times the change in concentration of B over the change in time. Okay, and that is equal to how fast the products are being made. Positive, you don't have to write the positive, but I'm going to just to make it stand out. 1 over lowercase c times the change in concentration of capital C over change in time. And I could also, if I have a second product, put 1 over D times delta D delta T. Okay, so to find the average rate of a reaction, we can use any of the species, reactants or products, whatever we're given, the change in the concentration over the change in time multiplied by 1 over the coefficient, and always make the rate a positive value. Okay, so if you get a negative change in concentration, you're going to multiply that by a negative 1. Okay, so that's how we find the average rate. Instantaneous rate is very similar. The instantaneous rate of the reaction is calculated very similarly. This one is not really seen on the AP test, but it's not too hard, so we'll go over it really quickly. So for our reaction up there, I'm just going to redraw down here what it might look like. The instantaneous rate is at a specific time. So this is time here, and this is concentration. I'm just going to put brackets for concentration and molarity. So if I picked a random time, like right here, at this time, whatever that is, what is the rate of change there? Okay, well, it's the slope at that point. It's easy when you're talking about a section, like from here to here, to find the slope of that part, because it's basically a line. But the slope at a point, some of you that might be in calculus might be recognizing that is, if I draw a tangent, which just touches at that point, it's going to be the slope of this tangent line. Okay, and the slope of a tangent in calculus, we would call that the derivative. So the derivative of this function at that point would be the rate. Okay, now we're not in calculus, most of us, and you don't have to do calculus for the AP test. So how would you find the slope at that point? You draw the tangent line, and then you're going to make a little triangle like this. Okay, pretend that's a perfect triangle. And we are going to use the average kind of between these 2 points right here. So instead of at that specific point, we have our initial and our T final. So let's say it goes from 10 seconds to 40 seconds. The change right here would be 30 seconds in that made up example. And we would look at the concentration right here versus the concentration right here. That's supposed to be a straight line. So to find the instantaneous rate of the reaction, it's still just the change in the concentration of, let's call it A, over the change in time. And we have to draw the tangent line first. So let's write this in steps because that was a lot of info. We are going to draw a tangent at given t, so whatever the given time is that we want. Okay, if that was 10 and that was 40, that would be like 25 seconds, something like that. So if it said, what is the rate at 25 seconds exactly, we would have to draw a tangent at 25 seconds. So draw the tangent at given time t, and then find the slope of that tangent, of that line. Okay, tangent line. And to find the slope, it's just going to be the same exact equation that we had up here. We don't have to worry about the coefficient because we are talking about whatever this red line is representing. So what is the rate of that red line at the given time? Okay, so we will come back to that later, but it's just the change in concentration. It's rise over run for the tangent line. Example 14.1, this is found on page 627, and it says we have the reaction of H2O2 plus 3I negative plus 2H plus yields I 3 negative plus 2H2O. Okay, so that is our reaction. It says in the first 10 seconds of the reaction, so delta T is the first 10 seconds, so from 0 to 10 is 10 seconds. The concentration of I2, oh, I'm so sorry. I don't know why I said 2. It's I minus. The concentration of I minus drops from 1.00 to 0.86. 8 molar. Okay, so we need to take 1 minus 0.868, 0.132. So the concentration changes by 0.132. The time changes by 10 seconds. A says calculate the average rate in this time interval. So the average rate, calculate the average rate of this reaction in this time interval. Okay, so the rate is going to be equal to the change in iodine over the change in time. But remember that we have to take into account the coefficient here. So let's make it a different color so we can see. This 3 right here, the coefficient, we have to put 1 over 3. And the concentration is decreasing, so I really should have written the change as negative 0.132. Remember that overall, we just need to get a positive value for the rate. So I'm not going to worry about that negative too much right now. It's going to be 0.132 molar over 10 seconds. That looks like a 2. That's a 1. And if we get, so again, with the negative thing, sorry if I confused you guys, it should have been the final concentration, 0.868, minus the initial concentration of 1. So I really would have gotten negative 0.132, and then I could put a negative out in front, and I would get a negative times a negative, which is a positive. And however you solve it, you should get 4.40 times 10 to the negative third molar per second. So that's how much the molarity is changing per second. Okay, part B says determine the rate of change in the concentration of H plus. So now we're looking at H plus during this time interval. So notice that it's a 3 to 2 ratio here. Okay, it's a 3-to-2 ratio. What we found was the rate of the reaction regardless of those coefficients. So it's for 1 mole of each of these things is what we found the rate of. So the rate with regards to H plus, let's put a little H plus here, is going to be the rate that we just found of that reaction times 2. Okay, so we're specifically now looking at the rate of H plus, not the rate of the whole reaction. So it's going to be 2 times 4.40 times 10 to the negative third molar per second is going to be 8.80 times 10 to the negative third molarity per second. And because this is a reactant, the concentration is going to be actually decreasing. So the rate of this guy is not the rate of the reaction. The rate of the reaction is always positive, but the rate of the reactant is actually going to decrease. It's going to go down. Okay, another way of looking at that would be if I plugged this number in red, the rate of the reaction right here. If I plugged that in, then I'm looking for the rate of change of the H plus. So I'm going to need more room. Let me scroll down. Do I have room at the very bottom? Yes, I do. So it would be the rate of the reaction is going to be 1 over that coefficient. That was 2. It's negative. 1 over the coefficient of my H plus, delta H plus over delta T. Okay, and this number right here, that's my 4.4. That's the rate of the reaction that we found in A to the negative third, negative 1/2. And this guy right here, let's do it in purple. Delta H plus over delta T, that's the rate with respect to just the H plus. So we can put rate of H plus. How do I solve for this purple one? Well, I'm going to multiply by -2 on both sides. Okay, so I would have -2 times 4.4, 10 to the negative 3 equals, if I multiply by -2 here, these are going to cancel out, and I get the rate of H plus. Okay, and this is going to be rate of H plus negative 8.8 times 10 to the negative 3. So we get the same answer, and I should have put the units there. It's molarity per second. So same answer either way. Hi, Simba. Okay, up here, let's do the for practice 14.1. Go ahead and try that one, and we'll go over it in a second. Okay, for practice for 14.1 says for the reaction shown in the example, predict the rate of change in the concentration of, we want the change, the rate in change of concentration of H2O2 now over delta T. We want that rate. And also, they also want delta I3 minus over delta T in the same time interval. So basically, since it's the same time interval, they're changing proportionally to their coefficients. So how does H2O2 compare? Well, since there's only 1 mole of the H2O2, it's going to be the same as the rate of the reaction. So this one, the rate of H2O2 is going to be 4.40 times 10 to the negative third molar per second. And the way that the I3 minus, the rate of the I3 minus is going to be, it's also a coefficient of 1. So the rate that it increases is going to be proportional to the rate of the overall reaction. 40 times 10 to the negative 3 molar per second. Let's check the back of the book and make sure we got that right. Okay, so checked in the back of the book and we are correct. The rate of the hydrogen peroxide and the I3 minus are the same as the rate of the reaction because they have coefficients of 1. Let's look at the conceptual connection. The conceptual connection says for the reaction A plus 2B yields C, under a given set of conditions, the initial rate, so the rate is equal to 0.100 molar per second. What is the change? So this is the rate of the reaction. That's, remember, for 1 mole of this reaction going, and it's always positive. What is the rate of B? Well, B is going to be used up twice as fast as A. So since A is the 1 mole here, that's how fast A is going to react. That means B is going to be twice that amount. So it should be, and B is decreasing. So the rate that it's going down should be this value. And let's see if we are correct by looking in the back. All right, that is correct. It's a negative value because it's a reactant, so the concentration is decreasing, and it's double the amount because it has a coefficient of 2. We will pick up right here at B tomorrow, and I will see you guys later. Have a great day.